And today I will talk about the rational Turán exponent conjecture by Erdős and Simonovich. This is joint work with Jae-Hoon Kim and Hong Liu from University of Warwick. So let me introduce with some brief terminology. So the extreme graph theory studies graphs that optimize graph parameters under certain conditions. And one of the basic and classical examples is to study the maximum number of edges in an n-vertex F3 graph. So here is the basic definition. So Ex and F is the maximum number of edges in an n-vertex graph with no subgraph in the family of graphs. So we simply write Ex and F if F consists of only one graph. So Mantel, in 1997, Mantel proved that if a graph, n-vertex graph with no triangle, has the maximum number of edges, then the number should be n squared over 4. So this is one of the most classical examples in extreme graph theory, and the extreme graph is unique. A complete bipartite graph with parts of the almost same size. And few decades later, Turán showed that if graph has no cliques of order R plus 1, then the extreme graph is so-called Turán graph, a complete R-partite graph with part of the size with almost the same size. So the extreme number is asymptotically has this value. But however, in general, we don't know the exact structure of extreme graphs, but we only know their approximate structure. So one of the fundamental theorems on their approximate structure is the theorem by Erdős, Simonovich, and Stone. Erdős and Stone in 1946 determined the asymptotics of the extreme number, and two decades later, Erdős and Simonovich determined their approximate structure. So let me state the theorem. So given a finite family of non-empty graphs, here non-empty graphs means a graph. So non-empty graph means the graph should have at least one edge. And let R plus 1 be the minimum chromatic number in a graph in F. Then the extreme number is asymptotically has this value. This is the result by Erdős and Stone in 1946. And 2 decades later, Erdős and Simonovich proved a stronger result, which determined the approximate structure on extreme graphs. So roughly speaking, if every n-vertex graph is almost extreme, which means it has the number of edges close to the extreme value, then it is close to the Turán graph, means the metric that measures closeness is symmetric difference. So that means if every n-vertex graph has the number of edges almost extreme, then there is some graph isomorphic to Turán graph such that their symmetric difference has very small size. So it is very close to Turán graph. But however, when F contains a bipartite graph, then R becomes 1. So the theorem only says the extreme number is little of n squared, so it is degenerate. So we call it a degenerate case. So for many of the case, people try to understand the extremal number when F contains a bipartite graph. But however, despite of their effort, we have only little information on the correct order of extremal number, even for well-known bipartite graphs. So, for example, a complete bipartite graph, KAIST, has the order of n to the 2 minus 1 over s when s is equal to 2, or both s and t are 3, or t is sufficiently larger than s. So the smallest example we don't know is K44. We don't know whether this is the correct order, even for this small graph. For even cycles, it is only known that for k equal to 2, 3, or 5, so extremal number of C2k has the order of n to the 1 plus 1 over k. And the smallest example that we don't know is the cycle of, so extremal number for an even cycle of length 8. And another example is three-dimensional cube graph. Exactly look like this. Which is three regular graph with 8 vertices, and Erdős and Simonovic proved that extremal number of three-dimensional cube graph has the lower bound n to the 2/3 and the upper bound n to the 8 over 5. But for many of the case, both lower and upper bound of extremal number have not been improved. So one of the problem is improve the lower bound and upper bound of extremal number of three-dimensional cube. So yeah, there is an excellent survey by Fred and Simonovic on these topics. So few decades ago, Erdős and Simonovic made many conjectures on this topic, and one of their major conjectures is which we call rational exponent conjecture. So the first conjecture is given a finite family of graphs, there is a rational number between 0 and 2 such that their extremal number is order of n to the q. And the second conjecture is somewhat stronger than the reverse of the first conjecture, which is for any rational number between 1 and 2, there is always a bipartite graph f with the extremal number is order of n to the q. And actually, there is no much progress on the first conjecture, but for the second conjecture, recently Buck and Colon proved the converse of first conjecture, which is slightly weaker than the second conjecture. Their theorem is given any rational number between 1 and 2, there is a finite family of graph with their extremal number being order of n to the q. And I will leave some remarks. So recently, when they published their paper on archive, Fitch extended, based on their idea, Fitch extended the result of Buck and Colon to uniform hypergraphs. So his theorem is that given any rational number between 1 to k, there is a finite family of k uniform hypergraph with the extremal number being order of n to the q. And the first conjecture of Erdős and Simonovic is false for K-uniform hypergraph when K is at least 3. So for hypergraphs, Lucha and Semerdy disproved Erdős and Simonovich conjecture on when K is at least 3. And here, the finite family, the finiteness is very important because for some infinite family, the first conjecture is not true. So, for example, if we exclude any irregular graphs, then their extrema number is between n log n and n log n. So there is no rational number q with satisfying this inequality. Hereafter, we focus on the second conjecture of Erdős and Simonovich.
Can I ask about the previous? So in the second column, then what is the range? K uniform hypergraphs. Second column of the remarks.
This one?
Erdős Simonovich's conjecture is false. So now the range is what? Q.
So what they prove is that
Could it be real? Irrational?
so-called
What
6-3.
would be the conjecture? What is the conjecture that is false?
Okay. So
Q should be what, between 1 and 3? Or
Q should be any rational number between. For any so the conjecture for K uniform hypergraph is that for any family of K uniform hypergraph F, there is a Q rational number Q between 0, 0 and K. Yeah, such that blah blah. But Lucha and Semerdy proved that this is literal and square, but always bigger than n to the 2 minus epsilon for any epsilon less than 2, no positive epsilon. So here F63 consists of triangles and one. So here the edge consists of this one, and so there are some other 3 uniform hypergraphs, but I don't remember. Yeah. So I will leave some remarks on the result of Buck and Colon. So to prove their theorem, they use so-called random algebraic construction, which was recently introduced by Buck. So in general, when you consider some random construction, many people try to rely on Erdős-Renyi model on random graphs, but instead of using Erdős-Renyi model, they considered a graph constructed by a set of algebraic varieties from random polynomials of bounded degree. And their method is quite useful to establish the lower bound of the extrema number when f is bipartite and having some repetitive structure in the sense of blowup, which I will explain later. So here, let me begin with some definition. So now we consider a family of graphs consisting of only a single graph. So here the real number is realizable if there is a graph F having the extrema number being the order of n to the r. So far, in contrast to the finite family of graph case, there are only few known realizable numbers. So for example, 1 and 2, and the number of the form 1 plus 1 over m, which is realized by Serre graphs, and this was proved very recently. So the upper bound of the extrema number of Serre graph was established by Faudry and Simonovich in 2 decades ago, 2 decades ago, but the lower bound So they couldn't prove the lower bound at that time, but using the box random algebraic construction recently, colon proved that the lower bound of the extremal number of Serre graph is the order of 1 plus 1 over m when k is sufficiently large. Here, the Serre graph, so I have not defined the Serre graph yet, but Serre graph is a generalization of even cycles. So here we have a path of length L, and Serre graph is constructed by attaching many paths with sharing the same end vertices. So here the width should be k. So this is Serre KL. So here this contains the even cycle of length 2L here. So people couldn't prove the people couldn't obtain the correct order of extremal number for even cycles, but they obtained the extremal number for Serre graphs. And the another realizable number is of the form 2 minus 1 over m, and which is realized by complete bipartite graph. So the upper bound was obtained by Kvaritsos and Turán, and the lower bound was obtained by Alon, Ronyai, Szabo by using so-called normed graph. And very recently, 7 over 5 was, so Jiang, Ma, Freeman found another realizable number, 7 over 5, realized by a graph called 3-comb pasting. And they also obtained infinitely many realizable numbers of the form 2 minus 2 over 2n plus 1, and realized by so-called generalized cubes. And actually, in his survey paper, Simonovic conjectured that the set of realizable numbers is dense in the interval between 1 and 2, which is somewhat weaker than the original Erdős and Simonovic conjecture. However, from these examples, the only known limit points in the set of realizable numbers are only 1 and 2. So we have made some progress toward Erdős and Simonovic conjecture recently, and they include our previous known result. So we proved that given any integer, positive integer a and b, with satisfying this equation, the number any number 2 minus a over b is realizable. And interestingly, as a straightforward corollary, this theorem gives infinitely many new limit points other than 1 and 2 in the set of realizable numbers. So this theorem implies that for any integer m, 2 minus 1 over m is a limit point in the set of realizable numbers. So yeah, this is only epsilon, so we resolve only an epsilon of the conjecture. Yeah, but yeah. So prior to explaining our main theorem, so we introduce some new definition. So in his paper introducing a random algebraic construction, Buck demonstrated to show the extremal number of complete bipartite graph has the lower bound n to the 2 minus 1 over s when t is sufficiently larger than s. And using his random algebraic construction, a few years later, Colon was able to show the Serre graph has the extremal number with the lower bound n to the 1 over n to the 1 plus 1 over L when K is sufficiently larger than L. And so in 1983, Faudry and Simonovic obtained the upper bound for the extremal number. So his result imply the Serre graph has the extremal number of the order of n to the 1 plus 1 over L when K is sufficiently larger than L. And finally, they generalized both results in the language of so-called rooted balanced trees. So thereby proved Ehrlich-Simonovic conjecture for a finite family of bipartite graphs. No, here, yeah, I have made mistake. Finite family of graphs. So because their family may contain non-bipartite graph here. So here we slightly extend their notion of rooted trees to rooted bipartite graphs because their proof for lower bound is also valid in this setting. So let me briefly introduce the definition. So here, for any bipartite graph and any proper subset of the Barrex set, so we say a tuple Fr is rooted on R, and R is the set of roots. Here, we may consider a local density. So, given a graph, here the set of root vertices, and for any subset S outside of root vertices, we want to consider any edges incident to a Barrex in S. So divided by the cardinality of S. And the global density is defined by the local density of R vertices outside of S. Outside of R. So, to give some intuition, when R is independent, which we'll mainly consider that case, so the global density is identical to the number of edges of the graph divided by the number of non-root vertices, because there is no edge between vertices in R. And we say the rooted bipartite graph is balanced if the global density is minimized among all the local densities. So here, there are some examples of rooted balanced trees. For example, stars. Stars here with here all leaves being roots. Yeah, it sounds so weird, but yeah, all leaves being roots, then it is clearly it is balanced because we only check this for when S consists of a single vertex. And for example, paths, when these two vertices become root vertices, then one can easily check that the path is a rooted bipartite graph. And yeah, both examples are often used. So we may consider some so-called blow-up operation on rooted bipartite graphs. So given any rooted bipartite graph, we may consider the else blow-up by taking L disjoint copies of F and identifying all root vertices. So here, let me give some example. So we have a fourth star, which is balanced rooted bipartite graph, with 4 roots, which are leaves, 4 leaves, and their blow-up is constructed by taking disjoint copy of 2 false stars, and when you identify each of root vertices, we have this graph. So what you can get is so this graph is isomorphic to complete bipartite graphs. So any blow-up of stars become complete bipartite graph. So what is the blow-up of the path?
What are the roots?
So roots are always n vertices of path here. Yeah, so the blow-up of path becomes Serre graphs. And one of the easy observation is that if a rooted bipartite graph is balanced, then so is its blow-up. So one can easily check that stars and paths are balanced, so the complete bipartite graph and Serre graph are also balanced. So this is an example. So given an S star and the set of root vertices on S leaves on the S star, then its blow-up is isomorphic to complete bipartite graph, and it is also balanced by the observation. So for example, for other examples, if F is a path of length L, then R is a set of n vertices, then its blow-up is isomorphic to Serre graph, and it is also balanced. So let me briefly state the precise result of Buck and Colon. So they constructed a finite family of graphs as follows. So given a rooted tree, so they only consider tree. So here, previously we discussed some rooted bipartite graph, but they only considered a rooted tree. So given a rooted tree, and consider any L copies of rooted tree of TR. Here, when we define the blow-up, we said the vertex set are disjoint except at the root vertices, but they allow the non-root vertices, so they allow some common non-root vertices. So they may share some non-root vertices, and their family is a collection of all these graphs, which is the union of these copies. Here, these copies, so TL consists of all of possible disunions, so they also include the blow-up of the tree T. And Buck and Colon also show that there is a balanced tree with the density B over A for any integer satisfying this. So this is the precise theorem which Buck and Colon proved. So given any rooted balanced tree with independent set of roots, there is some sufficiently large integer such that for any integer at least L0, the family TL constructed by S of O has the lower bound of this value. As a corollary, so given any rooted balanced tree with independent set of root vertices, we can say the extremal number of L's blow-up of T has the lower bound with this value. So this is obvious because this family TL contains this L's blow-up of T.
저기서 VTI 같은 non-rooted 럭티스를 아이덴티파이 할 때 엣지도 아이덴티파이 되는 거예요? 멀티 엣지도 되는 거예요?
Yes, yeah. All the no. So yeah, we don't consider. So here we don't consider. So we only consider simple graphs. So yeah, we just ignore some parallel edges. So here TL may contain some. So graph in TL may contain some odd cycles because they may share some non-rotated vertices. So when they blow up this path, maybe the path becomes like this. So yeah, they may share some non-rotated vertices. So we may identify this vertex to this vertex, and maybe then and identify our lucid vertices, then the graph may look like this. So this is included in some the family of in this setting. So they may contain some cycle of length 3. So what we observed is that in fact their proof would imply the following variation, which we often use. So previously Bloch and Kohler only consider rooted balanced tree, but we may consider any rooted balanced bipartite graph with positive global density. So for any given rooted balanced bipartite graph with positive density, there is some sufficiently large integer such that for any integer at least L0, the extremal number of blow-up of L, a blow-up of F, has the lower bound of this value. So what this proposition implies is that to show any given rational number is realizable, so first we find it's sufficient to find a rooted balanced bipartite graph F with this global density and just show the upper bound of extremal number is order of n to the q for sufficiently large L. Then with this proposition, we have that we are able to show that Q is realizable because this proposition gives the lower bound, which matches the upper bound here. So this is our strategy, and we may consider some balanced tree defined as follows. So given any T star, so we begin with a T star and so here leaves not, so my mistake, we attach S vertices to each of T plus 1 vertices of the star, and those S vertices become root vertices. So here, so here the figure depicts the blow of second blow of D43. So D43 is look like this. So begin with 4 star. We want to attach 3 vertices to each vertices. So 3 vertices. So 3. And those newly attached vertices become out of root vertices. So when we blow up this D43 second time, then we obtain the graph, bipartite graph look like this. And it is also rooted bipartite graph. And one can easily check that the DTS is balanced, so is blow up, and they have density global density of the form like this. And yeah, we are able to show that their extrema number has the upper bound of this. And using the previous proposition on lower bound, we are able to show that indeed the upper bound matches the lower bound. When L is much larger than both T and S. So our idea of the proof is first follows the leveling method introduced by Faudry and Simonovic 2 decades ago on Serre graph, and we use some variation of dependent random choice. And this proposition already implies that 2 minus 1 over m is a limit point in the set of realizable numbers because when we set S to be m here and send t to infinity, then we obtain that 2 minus 1 over m is a limit point in the set of realizable numbers. So this is our main proposition to prove our main theorem. So to obtain other realizable numbers, we introduce an operation so-called densification. So here the definition looks very formal, but I will briefly describe it by drawing a picture. So given any rooted bipartite graph, so here these are the two parts of the bipartite graph. They have some root vertices on both sides, and we have this rooted vertices, this rooted bipartite graph, and we want to consider the densification operation is like this. So we want to add two vertices, which is denoted by XNA, XB, and XA is adjacent to all non-root vertices on the part A, and XB is adjacent to all non-root vertices on part B. So here we obtain a new rooted vertices which we will call densification of FR. So one of the trivial observations is that the densification operation increases the global density exactly by 1. And one of our lemma shows that if a given rooted bipartite graph is balanced, then so is its densification. So what we're gonna be showed, so we introduce some new definition on realizable number. So a real number is balanced realizable if there is a connected rooted bipartite graph f and some sufficiently large integer such that their global density becomes 1 over 2 minus r, and their blow up has the extrema number of order n to the r for large L. And we are able to show that if 2 minus a over b is balanced realizable, then so is 2 minus a over a plus b. So when 2 minus a over b is balanced realized by some balanced rotated bipartite graph, then it is 2 minus a over a plus b is also realized by the densification of the rotated balanced bipartite graph, which relies 2 minus a over b. So this lemma follows by the definition of densification and the reduction theorem by Erdős and Simonovich. So yeah, because I have only little time, I will skip the proof. Yeah, but the proof is easily followed by the reduction theorem of Erdős and Simonovich. So using the proposition on DTS and densification lemma, we are able to show our main theorem. So for when a is equal to 1, 2 minus 1 over integer is realized by complete bipartite graph. So we may assume that a is at least 2. Then 2 minus a over a plus 1 is realized by fair graphs. And actually, 2 minus a over a plus 1 is balanced realizable because this value is equal to 1 plus 1 over a plus 1. So they are realized by fair graph with every path of length L plus a plus 1. So using the densification lemma, we obtain that 2 minus a over b is balanced realizable when b satisfies this condition. So for the other direction, dA minus 1, k minus 1, the blow up of dA minus k minus 1 relies this number. So we obtain the theorem. Actually, densification increased the density, global density of rotated bipartite graph by 1. So the one natural question is to introduce other operation which decrease the global density. So the densification increased the global density, so it is useful to obtain the bigger realizable numbers, but it is not useful to obtain smaller realizable numbers. So we try to introduce the operation that decrease the density. And one of the natural candidate is the subdivision of rotated bipartite graph. So here the subdivision is obtained by replacing all edges with internally disjoint paths of length 2, and they have the same set of root vertices. So previously, look at this figure. So given any 4 star, its subdivision replaces all edges by a path of length 2, but they have the same set of root vertices. So this is the subdivision of S4. So one of the easy observations is that if there, this is mistake. So if R is independent and F has the global density B over A, then its subdivision has the global density this way. So this is only valid when R is this is valid for any rotated bipartite graph, sorry. And our proposition is that given any rotated bipartite graph with global density at least 1, its subdivision is also balanced. So if the original rotated bipartite graph is balanced, then its subdivision is also balanced. So the next thing is try to So we try to prove some statement as well. So we say a graph is good when its extreme number has the upper bound order of n to the 1 plus alpha, and the subdivision has the upper bound 1 to the n to the 1 plus alpha over 2. So for example, a Serre graph is good. So their extreme number has the upper bound n to the 1 plus 1 over L, and their subdivision is isomorphic to the Serre graph of length 2L, which has the upper bound like this. So this is one of the tight example, and we conjecture that every graph F is good. So the conjecture looks some random conjecture, but it has some motivation. So suppose F has the extreme number like this, and given any graph G with sufficiently many edges, it contains a graph with minimum degree like this by just removing a vertex of low degree. And we may consider a graph H star, which is so-called neighborhood graph, which has the same set of vertices, and xy is an edge of H star if there is a vertex between x and y. And using some lemma from using some dependent random choice, we are able to obtain that the H star has an edge n to the 1 plus alpha. And so by our assumption, H star contains F as a subgraph. And the copy of F, so F copy in H star may correspond to the subdivision of F in G when the copy is not degenerate, which means, so one subdivision, so if we subdivide a graph once, then every edge becomes a path of length 2. So we add some new vertex inside each edge, but if the copy is degenerate, then these newly added vertices may overlap. So in that case, we cannot say the subdivision of F is a subgraph of H, but if the copy is not degenerate, then we can say the subdivision of F is a subgraph of H, so it's a subgraph of G. So if we are able to show there is always a non-degenerate copy of F in S star, F in H star, then we are able to show this bound, so prove the subdivision conjecture. But we couldn't show there is always a non-degenerate copy. Yes, this is one of the motivation, and the reason why we introduce this conjecture is the conjecture weaker than this conjecture. So we able to show that the weaker version of this conjecture implies Erdős-Simonovic conjecture. So let's consider some family of connected rooted balanced bipartite graphs. So F0 includes all stars rooted on leaves, and they are close. So it is close under taking subdivision and taking densification operation, and we may consider the minimal family that satisfy these three conditions. And the conjecture is that a large blow-up of graphs in this family is good, and we are able to show that this weaker version of subdivision conjecture implies Erdős-Simonovic conjecture. So it seems doable than the strong subdivision conjecture. But nevertheless, so here the the basic graphs so the F0 is constructed by including all stars, but we could not prove this weak version of conjecture for stars. The conjecture, so the blow-up of stars is a complete bipartite graph. So this conjecture suggests that extreme number of the subdivision of complete bipartite graph has the upper bound of the order of n to the 3/2 minus 1/2s. But we're only able to show this bound based on the proof of the proposition of DTS. Actually, this is the best known bound for the subdivision of KST. So Alon, Krivelevich, Sudakov showed that the subdivision of KST has the upper bound n to the 3/2. And very recently, Lee and Colon showed that it has the upper bound n to the 3/2 minus 1/12t. And a few months later, Jenger succeeded in proving this bound, which is the same bound of ours, but actually his proof is based on the proof of Lee and Colon, which is very different from our proof. So let me end with some further remarks and open problems. So actually we extensively use the densification lemma, which is effective in getting realizable numbers close to 2. So we want to find some realizable numbers which is very close to 1. So, but the rotated balanced bipartite graph with small density, so the density close to 1, tend to be sparse and have large radius. So, and we believe the following statement. So this is the graph HTS, so which has a large radius than DTS when S is sufficiently large. And we believe that this equation holds. But we could not prove this bound because our method is only applicable to the rotated balanced bipartite graph with small radius. And the second problem is the subdivision conjecture for complete bipartite graphs. So we think it is very important to prove this because we have tried to show the weak subdivision conjecture for many other examples than the subdivision of KST, but all these examples have the issues similar to the subdivision of KST. So we think that verifying this problem would give some insight to resolve the weak subdivision conjecture, which will lead to solve the Erdős-Simonovic conjecture. And our third remark is some phase transition of blow-ups and rotated bipartite graph. So the lower bound of Buck and Colon is only true when the number of copies in a blow-up is very large. For example, so when you consider D21, then when T is sufficiently large, then this bound holds. But when T is very small, for example 2, then we obtain significantly lower bound. So yeah, this is a reason of this. And the blow up of the graph, so the phase transition happens when the number of copies of T is larger than 2 here. And this contrasts to the well-known conjecture for even cycles like this. Why? So the blow up of a rooted path is isomorphic to Serre graph, and the even cycle is a second blow up of rooted path. So the even cycle conjecture, this is the even cycle conjecture, suggests the transition already happens when L is equal to 2. And recently, Burstert and Williford obtained this bound. So they obtain so this is, there are 3, 4, and they obtain the bound on the extremal number of theta 3, 4 is exactly this. But actually, we don't know the extremal number of C8. So C8 is this. So if we add a single path, if we attach the single path on the cycle of length 8, then we obtain the type bound, but we still don't know about the even cycle of length 8. And second question is, so we want to ask, is there any method to capture this phase transition happens in blow-up of a rotated bipartite graph? But the method, random algebraic construction by Buck and Cohn, Buck, is not delicate to capture this phase transition. So we hope that this method will be developed in the future. Thank you.